Hello, Hornets. Today we're going to be taking a look at two very special types of related rates. Up to this point, we've seen the right triangular related rate, and today we're going to be taking a look at related rates that require similar triangles or a linking equation, perhaps, with which to find our solution. So let's start off with our first one. This is a very common problem. A conical tank with vertex down is 10 feet across the top and 12 feet deep. Water is flowing into the tank at a rate of 10 cubic feet per minute. Find the rate of change of the depth of the water when the water is 8 feet deep. So the first thing we're going to do is I'd like you to draw a picture. Pictures are important to us. We are visual creatures. We have been for our entire life. Being able to see predators and the problems happening around us. We just generally do better when we see a picture. So try and draw a picture. Now you'll notice we have our radius up here, which is 5, and we have our height or depth, which is 12 feet deep. So 12 is right here. Now, as we do this problem, one of the things that you have to remember is they do not give us everything we want. For example, we know that if we have v equals 1/3 pi r squared h, then if we were to try to do our implicit differentiation, we're going to have the product rule here. And this would give us 2/3 pi r h r prime plus 1/3 pi r squared h prime. And in this, if we categorize what we are given, we have our v prime, and our v prime is 10 cubic feet per minute. But they've also given us a depth, which is our height, 8 feet. And then they've given us the question, what is our rate of change of height? Well, unfortunately, if you look at this, we don't have enough information. And so what we have to do is we have to look at this as a similar triangle. And we're going to have a radius here, which we don't know. But we do know our height is 8 feet. And it is with this similar triangles that we're going to be able to create 12 is to 5 as our radius is to our height. And if I'm working with this, I then know that I can multiply and I can find my radius is 5/12 the height. Or I can work with my height is equal to, what would that be? R to the reciprocal, so let's just take the reciprocal 12/5 R. Well, if that's the case, then I know R prime is going to end up being 5/12 H prime, and I can now substitute it in that. But what's more important is I can substitute in the R in the original problem. Here, take a quick peek. If V is 1/3 pi R squared H, then I can put my 5/12 H inside, and I can find that V equals 1/3 times 25 1/44 times pi H cubed. And you notice, now I don't need to have any other information. I don't have to replace R prime, and I don't have to replace R. I can replace it in the beginning. Now, this is called a linking equation, an equation that we can use to replace information that we don't have in a formula. We see this a lot in our related rates. We see this a lot in what is also referred to as optimization, an application of derivatives. So now once I've got this, I can now take my derivative and find that v prime is actually just 25 1/44 pi h squared h prime. And now I can solve for my h prime. Notice h prime is simply going to be our 10 cubic feet per minute multiplied by the 144 divided by 25 pi, and we have our feet squared. So these feet squared are going to reduce, and I'll be left with feet per minute. And it's at this point that that's going to be my answer as soon as I simplify it, and I can reduce things, cleaning it up, whatever it might be. So you'll notice this is our first basic process. Being able to manipulate our formulas and doing so with this similar triangle, which allows me to get a proportion, and it is that proportion that gives me H or R. Let's take a look at one more. Now, this is the other classic AP Calculus problem that involves similar triangles. A man, 6 feet tall, walks at a rate of 5 feet per second away from a light that is 15 feet above the ground. When the man is 10 feet from the base of the light, at what rate is the tip of his shadow moving? So what we need to do is draw a picture again. There's my lamp post, the ground, and this is going to be my 6 foot tall individual walking away. And I'm just going to go ahead and draw my right triangle. After all, the tip of his shadow is right here, and that tip is relative to the lamppost. Where this gentleman is approximately 10 feet from the base of the lamppost. And here we have the shadow. So let's just look at what we've got. The two triangles are right here and here, 6 and 15. But if this is y and this is x, then this becomes y minus x. Now we could always say that we have x and y, and this is going to become x plus y. It's irrelevant. It's just setting it up so that we can get two triangles and work with our relationship. 6 is to 15 as y minus x is to y. Now with this, I'm trying to differentiate, but in order to differentiate, I can only differentiate in terms of one variable, and it has to be repeated only once. So I have two y's here, so I need to get to one y. Now we've done this through the manipulation in our algebra classes. You've also done it earlier this year. So what we're going to do is we're going to cross multiply and get 6y equals 15y minus 15x. Now please understand, cross multiplication really doesn't exist. I've mentioned that before. We're multiplying by the reciprocal on both sides. So we multiply by 15 on both sides, and we end up with 6. We multiply by y on both sides, becomes 6y, and we have 15 times y minus x, which I distributed. So I'm going to subtract 15y on both sides. I'm getting negative 9y equal to negative 15x. And then when I simplify, my y is equal to 5/3 x. This can now be differentiated. I couldn't differentiate it here because there were too many y's. But now I can. In terms of time, dt, my y prime, is equal to 5/3 x prime. Well, now we've got to go back and we've got to look and decide, well, what is the x prime? The man walks at a rate of 5 feet per second away from the light. So that's x prime. X is 10 feet. X prime is 5 feet per second. And because the individual is walking away from the light, that 5 feet per second is going to be positive. So I'm going to take that 5 feet per second, I'm going to put it right here, and y prime has to equal 25/3 feet per second. And that is now the rate at which the tip of his shadow, our y value, is changing, y prime. Now, if I want the length of the shadow's change is y minus x. And keep in mind that if I take the derivative, d dt, of y minus x, I end up with y prime minus x prime, and I have y prime here, and I know what my x prime is from the original equation. And a quick substitution and subtraction will yield an answer for that. Now, the only other options that we have with these types of questions are angles, and we've talked about those. So please be aware, we'll continue to look at them. But that's related rates working with similar triangles. I hope it helps, and I hope that you find this to be a useful tool. Thank you very much, Hornet.